Welcome back. In this video, we're going to look at what we call stoichiometry. Stoichiometry uses the molar ratios of chemicals in a reaction in order to determine the amount of reactant needed to make a certain amount of product, or the amount of product that would be produced from a certain amount of reactant. This requires that we're able to convert between moles, mass, concentration, volume, pressure, and number of atoms or molecules. And I'll introduce you to using what we call the table method as a way to help organize your information and solve these types of problems. So stoichiometric calculations always rely on the proportion or the ratio of moles of reactants and products as derived from the stoichiometric coefficients in the balanced chemical equation. When we take a look at our reactants and our products, we can talk about the reactants in terms of the amount and the number of moles. We can use the molar mass to convert from moles to mass. We can we can discuss the concentration, whether that's of a solution, whether that's within a mixture. And that could be concentration in terms of molarity or parts per million or mole fraction or mass fraction. Using the ideal gas law, we can relate to the volume and pressure of a gas. And we can discuss the same information for the products of a chemical reaction. The bridge in between the reactants and the products is the stoichiometric proportions, or the coefficients of a balanced chemical equation. And by understanding how to use those coefficients, we can relate the amount of moles of reactants to the amount of moles of products. It's not possible to easily relate the mass of reactants to the mass of the products, or the pressure or the volume of reactants to the pressure or volume of the products. The fundamental currency of chemistry is moles. And so for all chemical reactions, your instinct should be to take whatever information you are given and convert it into moles of that substance and see how those reactants interact with each other to produce the products. So again, you need to be familiar with how to make the connections in between solution concentrations, between masses, between moles, between pressure or volume of an ideal gas. And you need to be able to do that quickly to solve these types of problems. So let's go through an example. Let's say that you have a clean engine that burns a gallon of gasoline. We want to know how many kilograms of carbon dioxide will it produce. Let's make some assumptions. Let's assume that the gasoline is entirely octane with a density of 0.692 grams per milliliter. And we know as well that a gallon is equal to 3.79 liters or 3,790 milliliters. So what do? There is a multi-step process that you can use when solving problems that involve stoichiometry, that involve chemical reactions and converting reactants to products or products to reactants. The first thing to do is to write out a balanced chemical equation. Then we can organize the information into a table. We call this the initial change final table. And this helps us to keep the information organized and to make sure that we are looking for the right pieces of information. Within this table, we want to note whatever initial conditions were given. So for us, we are given information about the number of gallons of gasoline. We need to make connections between those initial conditions to moles, and then we need to find the moles. So this might be using the molar mass. If we're given the mass of a substance, this might be using the molarity and volume. If you're given either of those, this could be using the ideal gas law if you're given the pressure or the volume of a gas. When we calculate the change, the amount of reactant used up and the amount of product produced, this must always be in moles, and we need to make sure we're accounting for the coefficients from the balanced chemical equation. Then solve the problem, and it helps to fill in the table as we're going to make sure that we keep track of the information that we are using. We'll need to convert to whatever our final unit should be, making use of the appropriate connections and conversions, and then verify that our answer is reasonable. As you're going through this process, it can help to ask and answer 3 questions. What information do I want to find? What information am I given? And what information that I'm not given do I also need to solve this problem? So let's move on with this question. The first step, again, was to write out a balanced chemical equation. So I'd like for you to practice this. What would be the coefficient in front of the water for the balanced reaction of the combustion of octane? This is the reaction that we would need. So you need to be able to predict what the products would be and to write out the balanced chemical equation. Pause the video and try and do this. Welcome back. So we know for a combustion reaction that we're going to take octane in this case, react it with oxygen to produce carbon dioxide and water. When we balance chemical reactions, we want to start with an element that shows up on the reactant side only in one place and on the product side only in one place. So we could start either with hydrogen or with carbon. Let's start with carbon. To balance for carbon, we need 8 carbons on the right side because we have 8 on the left. To balance for hydrogen, we need 9 hydrogen, not a coefficient of 9, because there are 18 carbons in octane, and so we need 18 total out of the water. And then to balance for oxygen. Here, the simplest way is to multiply by 25 over 2, because there are 25 oxygens on the right side of the reaction, and each oxygen molecule itself contributes 2, so we need to multiply by 25 over 2. Then we want to balance and make only whole numbers, so we multiply everything by a coefficient of 2, which gives us 2 octane, 25 oxygen, 16 carbon dioxide, and 18 water. That's our balanced chemical equation. Now, I've made a table for us, and we need to obtain values in moles. In order to find the moles of our substances, we're going to probably need to rely on the molar mass. We're not dealing with gases and with volumes of gases, so the ideal gas law won't be applicable here for the octane. But we are given the volume of a liquid, and so we know the density of the gasoline, we know its volume. Therefore, we could use those to find the mass. And then using the molar mass, we can find the moles. So let's ask the question, what are we trying to find? We're trying to find the mass of carbon dioxide produced. The information we have is the volume of the gasoline, the density of the gasoline, and the balanced chemical equation. What else do we need? Well, we need to, if we want to find the mass of carbon dioxide, we need to know how many moles of carbon dioxide. To find out how many moles of carbon dioxide there are produced, we need to know how many moles of octane there were used up. To find the moles of octane, we need to find the mass of octane. And so we will need the molar mass, the mass of octane. And we can find the mass of octane by using the density of octane and the volume of the octane in gallons. So let's start by finding the mass of octane. This is found by taking the volume and multiplying by the density. We get 2,623 grams. Let's put that into our table. Now to find the moles, we're going to need the molar mass. When you add up the masses of carbon and hydrogen, you get about 114 grams per mole. So to find the moles of octane, we take the mass of octane and we divide by the molar mass to get just over 23 moles. This is our initial amount of octane. And what we would see then is that we're going to use up all of that octane. It's going to burn and have none left over, and it's going to produce some amount of carbon dioxide. Now, notice that it's not a 1-to-1 ratio of octane to carbon dioxide. So we need to multiply by that ratio in order to find the number of moles of carbon dioxide actually produced. So we take our 23 moles of octane and multiply by the stoichiometric ratio, the coefficients that are from the balanced chemical equation. And the balanced chemical equation shows that we produce 16 carbon dioxide for every 2 octane. That would mean that we would produce just over 184 moles of carbon dioxide. We started with none. We're going to add 184, and so our final moles is 184.07 moles of carbon dioxide. To find the mass of carbon dioxide, we need to use the molar mass. And so we take the moles of carbon dioxide, multiply by the molar mass, and we get just over 8,000 grams. Converting to kilograms, we get 8.10 kilograms. And that's our final answer. Now, we want to evaluate, does this answer make sense? Is it reasonable? Well, so let's think about this. We started with just about 2,500 grams of octane from our initial calculation. When you compare the molar masses of carbon dioxide to octane, we see that octane is much heavier. In fact, it's about 2.5 times heavier than carbon dioxide. So just based on the molar masses, we might expect about 1,000 grams of product. However, we see that the molar ratio is 1 octane for every 8 carbon dioxide. And so we need to multiply this mass by a factor of 8. And so we would estimate somewhere around 8,000 grams of our carbon dioxide, which is really close to what we actually calculated. So this seems reasonable. Another way to identify the whether or not the answer makes sense is if we knew the mass of oxygen that was used and the mass of water that was produced. The law of conservation of mass states that the mass of the reactants should add up to be the mass of the products. And so if we knew how much oxygen was used, then we could also compare in that way. So that's it for this video. Thanks for watching. Have a great day.